Then there are 3 sections in the book, the content of which are part of this course, but which we do not discuss extensively in this course, because you know the content in a different form from the previous course, Microeconomics 2. And these 3 sections are 8.6, which deals with continuous actions. So what if you, as a player, you do not choose between left or right, or you have 10 possible actions, but you have a continuum of choices. So you have a continuous action space, for example, if you need to choose a price, or as a firm when you need to choose a quantity. Section 8.7 deals with sequential games. So what if players do not choose simultaneously at the same time, but the action of player 1 is followed by the action of player 2. And player 2, in deciding, can take into account what he or she has observed player 1 doing. And then in section 8.8, repeated games is a topic. So what if players do not meet each other only once to play a game, but they play the same game repeatedly with each other? But as said, I don't discuss these sections explicitly here. I will continue with 8.9, which is about a new topic, games of incomplete information. And although this is all very logical, it may not be straightforward if you first deal with this topic. So what is the situation? Some players in the game now have information that other players do not have. And the players that do not have the full information, they will try to use what they do know to make any inferences about what they do not know. So this is quite secretive language, but I will become much clearer in what follows. So what we will do is quite simple. We focus on simple games with 2 players, and we assume that player 1 has private information, something that player 2 doesn't know, and all that player 2 knows is also known by player 1. And private information into game theory is modeled by introducing player types. So, and there are 2 flavors. So in section 8.10, and that's the part that we are going to discuss in this course, is when both players move simultaneously, but one of them has private information. And then section 8.11 of the book deals with so-called signaling games, where the player which has more information moves first. So, and that's signaling games are covered in the Master of Economics. So if you're interested in that, you still need to wait a bit. But I can assure you that 8.10, games of incomplete information where both players move at the same time, is already very interesting and leads to new insights. So the setup is as follows. We have a 2-player game. They play at the same time. And player 1 has private information and player 2 has not. And we model the private information by introducing player types. So player 1 can be a number of possible types T, and he or she knows his or her own type and also can condition on it in making choices. And player 2 is uncertain about the type of player 1, but must decide which strategy or action to choose based on her beliefs on the type of player 1. So this game begins at a chance mode, meaning that nature will decide the type of player 1. So nature draws a type from a set of possible types T1 till, say, Tk. And the probability that player 1 is of a certain type is information that's known also to player 2. So the probability that player 1 is of type Tk is Pk. Player 1 observes the type that is drawn, and player 2 does not observe this, but does observe the probabilities. So this is also the situation where I, as an instructor, I need to find out whether students cheat. I don't know, I don't observe whether a student is of the cheating type or not, but I do have some idea of the probabilities, saying, for example, that maybe 10% of all students is of the cheating type and 90% is of the sound non-cheating type. I must confess that I don't know, don't even know the exact probabilities. I'm even in the dark about that. I don't know whether it's higher than 10% or lower than 10%. I hope it's as small as possible. Okay, but that aside, player one observes the type before he will move, so he can condition his strategy on his type. So we denote the strategy of player one as a function of his type as S1-2. And player's two strategies is an unconditional strategies. So, and the type of player one may affect the payoff of player two in two ways. In a direct way, because he's of a certain type, and also in an indirect way, being that, well, being of a certain type influences the strategy of player one, and that in turn impacts the payoff to player two. Let's do a simple example. So we have two players, and now player one is of type T is 6 with probability 1/2, and type T is 0 with the other half probability. Meaning that the payoff matrix, as we know it, player one knows the full payoff matrix, but player two is in the dark about the exact value of the T over here. So with probability 1/2, T is equal to 6. With probability 1/2, it is equal to 0. And player one knows the value of T. So yeah, we can write this game instead of in matrix form also in extensive form. So that looks as follows. First, we have this draw from nature, drawing the type of player one. Then this is the decision nodes of player one. Player one can condition his or her strategy on his or her type because he observes the type that is drawn by nature. But player two, at the decision node of player two, we have this dotted area around it because player two does not know whether he at which node he is when making the decision for left or right, because he doesn't know the realization of the type of player one. So all four player two's decision nodes are in the same information set, because she does not observe player's one type before she has to decide what to do. And, well, what we learned in the course is to find an equilibrium, a Nash equilibrium, and the type of equilibrium that we need to find in games of incomplete information are called Bayesian Nash equilibrium. And again, the equilibrium requires that for player one, the strategy that he chooses in equilibrium is the best response to for each and every one of his types. So he needs to decide, okay, if I'm of type 0, what's the optimal thing to do? And if I'm of type T is 6, what is the optimal thing for me to do? And for player 2, player 2 maximizes an expected payoff because he knows the probabilities that player 1 is of a certain type, but he doesn't know exactly which type player 1 is in a given instance. So she needs to take the expectation with respect to the belief she has about player 1's type. And that brings us then to the formal definition of a Bayesian Nash equilibrium. So that's the solution concept that we apply here. And a strategy profile S1 T star as 2 star, where we observe that the strategy of player 1 is a function of, is conditioned upon player 1's type. This strategy profile is a Bayesian Nash equilibrium pair of profiles if it holds that for all types of player 1, the utility that the player 1 derives, of the player 1 of a certain type derives from playing that particular strategy is at least equal to the payoff that he would receive if he would play any other strategy. And for player 2 takes an expectation and maximizes an expected payoff. So the equilibrium strategy of player 2 must satisfy the condition that the expected utility payoff of playing that strategy is at least equal to the expected utility that she would derive if she would play any other of her feasible strategies. So, and these other feasible strategies are denoted as 2 prime. So again, the solution concept is very much in line to the concept that we saw before with the mixed strategy equilibria, except that now one of the players has private information about his type. Okay, so let's return to our two-player example where both have 2 possible actions and player 1 can be 1 out of 2 types. So player 1 can be of type T is 0 or T is 6, and each of these types is drawn with probability 1/2. And player 1 knows exactly which matrix he faces. He knows, okay, I'm of type T is 0, so this is the matrix that we face when we need to make a choice. If he observes that he is of type T is 6, then he knows that this is the relevant payoff matrix of the game. And you can see that, well, if player 1 is of type T is 0, then it's optimal for him to play D, down, always. Because that's the dominant strategy in this case. 2 is more than 0, 2 is more than 0. So independent of what player 2 will decide, it's optimal for player 1 to play down if he's of type T is 0. If he is of type T is 6, well, then his optimal response to player 2 playing left is to play up, because that gives a payoff of 6 instead of 2. But if player 2 decides to play right, then it's the optimal response of player 1 is to play down, because 2 is more than 0. This leaves us with 2 possible candidates for Bayesian Nash equilibrium in pure strategies. And note that I've underlined pure here because we're first going to look at equilibrium strategies where none of the players mixes between actions. So player 1, conditional on his type, will play one action with probability 1, and player 2 in such an equilibrium will also choose an action with probability 1. So the first candidate is where player 1 plays down if T is 0, because that's the dominant strategy when T is 0, and he plays up when he's of type T is 6. And player 2 plays L. Now it's clear that given that player 2 plays L, it is indeed optimal for player 1 to choose the actions exactly like this. To go for down if he's of type 0, and if he's of type 6, then it's optimal for him to play up, because 6 is more than 2. However, what about player 2? Is it really optimal to play L given that player 1 plays this strategy? Well, we need to look at the expected payoff of player 2. And if player 2 will play left, then his expected payoff, given what player 1 does, is he receives a payoff of 0 if player 1 turns out to be of type 0, which happens with probability 1 minus P6, because in that case, player 1 will play down and player 2 will be left with a payoff of 0. With probability P6, player 1 is of type T is 6, in which case player 1 will play up. And if player 1 plays up, the payoff to player 2 will be equal to 2 if player 2 plays left. So the expected payoff to player 2 in this case is 1 if P6 is equal to 1/2, as we have assumed. So could player 2 do any better? So is this really a Nash equilibrium strategy of player 2, or can he benefit by unilaterally deviating? Now, he has only 2 actions, so if he doesn't play L, the only way that he can deviate is to play right. Let's compute the expected payoff of player 2 if he plays right, given that player 1 strategy is still unchanged. Well, in that case, he would receive a payoff of 4 if player 1 happens to be of type T is 0, which happens with probability 1 minus P6, because in that case, player 1 plays down, player 2 plays right, and the payoff to player 2 is equal to 4. However, if player 1 is of type T is 6, which happens with probability P6, then the payoff to player 2 is 0, because then player 1 will play up. Well, if player 1 plays up, then the payoff to player 2 of playing right is 0. And the expected payoff, if we again assume that P6 is equal to 1/2, is equal to 2. And what we observe is player 2 playing L, given the strategy of player 1, is not optimal here. He can do better by deviating to playing right, because the expected payoff of playing right is more than the expected payoff of playing left. So this candidate is ruled out as a Bayesian Nash equilibrium. However, we fortunately have a second candidate. And the second candidate is where player 1 plays down if he is of type T0, because that's the dominant strategy to player 1 in that case, and where he also plays down if he is of type T is 6. And player 2 plays right. And this is a Bayesian Nash equilibrium. It's easy to see because, well, player 1 now plays down always. And then, well, for player 2, it's optimal to play right. Because, well, if player 1 plays down always, then player 2 gets 4 if he plays right, if player 1 is of type T is 0. And if player 1 is of type T is 6, then playing right also gives a payoff of 6 instead of 0. So player 2 cannot do any better than playing right. And also, given that player 2 plays right, it's always optimal for player 1 to play down, because 2 is more than 0, 2 is more than 0. So this is a Bayesian Nash equilibrium of this game. And then we can ask the question, okay, but for which values of the probability that player 1 is of type T is 6 is our first candidate also a Bayesian Nash equilibrium? And that's a question for you to answer. And you know that in order for this one to be a Bayesian Nash equilibrium, so why did it fail to be a Bayesian Nash equilibrium for P is equal to 1/2? Well, the reason was that at P is 1/2, the expected payoff of a deviation for player 2 exceeded the payoff of sticking to the agreement. So what we need to have is that this expression over here is at least equal to this expression over here. So we can equate the two, solve for P6, and we get an answer to our question. And the answer to our question is, if P6 is at least equal to 2/3, then candidate number 1 is a Bayesian equilibrium of our game. So Another way to show this is the way it's done in the book. So we have two possible equilibria. So player 2 has only two options, left or right, and player 1 has the options up and down, but in addition can also condition on the type. So he has 4 flavors. He can go for up always, he can go for down always, and he can decide to go for up if he's of type T is 0, down if he's of type T is 6, or down if he's of type T is 0, and up if he's of type T is 6. And we can rule this out because up is never the best thing for player 1 to do if he's of type T is 0, because then playing down is a dominant strategy. So these are in gray, we don't have to consider them, and we are left with the 2 over here. Now we can easily see that given that this is the strategy of player 1, it's optimal for player 2 to choose right. And so these are the expected payoffs to player 2. And given that player 1 follows this strategy, it's only optimal for player 2 to choose left if 2 times P6 exceeds the value 4 minus 1 minus P6. So it's the same thing as what we derived here, but that in the form of a table as is presented in the book as well. And now the most difficult question of this lecture, and it may be on the top of your mind right now, are there also Bayesian Nash equilibria in mixed strategies? So equilibria where one player has private information and one or both players mix over their possible actions. It's a great question, and the answer to the question is yes. And we're going to find them. So we will introduce a different solution concept, and this solution concept makes use of strategic form games. So we know them by G star. And in the strategic form games, each type of a player is presented as a separate player. So instead of having 2 players, we now have 3 players because each type of player 1 will be represented by a separate player. And a Bayesian Nash equilibrium of a game of incomplete information is a Nash equilibrium of the associate strategic form game. So notice that we here fiddled in the concept of strategic form games into our definition of a Bayesian Nash equilibrium, because now we consider Bayesian Nash equilibria in mixed strategies. So how does it work? We continue with our example that we just considered. So we have now 3 players, player 2, and importantly in the way that we are going about it is that the choice by player 2 will determine the payoff matrix. And the types of player 1, so either type T is 0 or type T is 6, will determine the rows and the columns. So, and we will do the general case. So we are agnostic about the probability with which player 1 is of type T is 6. We say, okay, player 1 is of type T is 6 with probability P. And this is what I mean by saying that the choice of player 2 determines the payoff matrix. So we have 2 possible choices. Suppose now that player 2 plays left, then we have the payoff matrix that is given here, where the rows and the columns are determined by player 1 being of type T is 0 or player 1 being of type T is 6. Now, so let's go through a number of these entries. If player 2 plays L, then we are here. If player 1 is of type T is 6, then player 1 will get a payoff of 6 if player 1 then plays up. If this player 1 plays down, he will receive a payoff of 2. If player 1 is of type t is 0, he plays up and player 2 plays L, then the payoff to that player will be equal to 0. And if he's of player type 0 and he plays up, so in player 1 is of type 0, but that doesn't really matter. So then his payoff is also equal to 0. And to player 2, if player 2 plays left, then the payoff is equal to 2 if player 1 is of type t is 0 and plays up. And also if player 1 is of type is 0 and plays up. And important is what happens here. So if player 1 of type t is 0 plays down, but player 1 of type t is 6 plays up, what is then the expected payoff to player 2 of playing L? Well, his payoff is equal to 2 if he meets player 1, because player 1 will play up, and that happens with probability p, because player 1 is of type t is 6 with probability p. If it happens that he meets player 1 being of type t is 0, well, then we know from this entry that that type will play down. The probability that he meets that type is 1 minus p, and in that case he will get a payoff of 0. So 1 minus p times 0 is 0. So the expected payoff of player 2 playing L, given that player 1 of type 0 plays D and player 1 of type t is 6 plays up, is identical to the probability that player 1 is of type t is 6, in which case player 2 will receive a payoff of 2. Now, for example, this one is easy. If player 1 plays down always, either when he is of type t is 6 or type t is 0, then the payoff of player 2 of playing L will always be 0. And then there's a second matrix which is conditioned on player 2 playing right. So let's do, now for example, this entry over here. If player 2 plays right and player 1 plays down if he's of type t is 0, then the payoff to player 2 will be equal to 4. So the expected payoff is 4 times the probability that player 1 is of type t is 0, which is identical to 1 minus p. At this entry, player 1, if he's of type t is 6, will play up. Well, if player 1 plays up, then the payoff to player 2 of playing right is equal to 0. So the expected payoff of player 2 of playing L or playing R, given that player 1 chooses as follows, given the type he is 4 times 1 minus p. And in this way you can fill all entries of both matrices. So now we have the payoff as entries in the of the 3 players as entries in the payoff matrix, and we can solve for the Bayesian-Nash equilibrium. So at the top I just repeat what's at the bottom here, and then we go to solve the best response of each of the 3 players. So for example, player 1 of type t is 6, given that player 2 plays L and player 1 of type t is 0 plays up, needs to decide, okay, what is optimal for me to do, up or down. Up gives me a payoff of 6, down a payoff of 2, so it's optimal for me to play up. And also here 6 is more than 2, so it's optimal to go for up. If player 2 plays right, it's optimal for me to play down. So there's a line here. It's optimal for me to play down. So there's a line here. Similar for the player 1 of type T is 0. He compares 0 and 2. It's optimal to play down if player 2 plays L. And also here. And you can see that the entries, these two are always identical because the payoff to player 1 when he's of type T is 0 doesn't depend on what he does if he would be of the other type, because he knows that he is not of the other type. So these two entries are always identical. These two entries are always identical. Same here. And also for the player 1 type T is 6 player, the two 6s here are always identical. These two entries, the 2s, are always identical because the payoff of player 1 when he's of type T is 6 do not depend of what he would decide if he were of the other type. And we then also need to consider what's optimal for player 2 to do, playing left or right. So player 2 will compare the 2 here to the 0 here, because that's what is optimal for me to do given the strategies of the player 1 types. Now 2 is more than 0. Here he needs to decide, okay, left gives me an expected payoff of 2p. Choosing right gives an expected payoff of 1 minus p. What is more? Now that depends on the value of p. And also here, now this one is easy. So 0 is less than 4. So given the strategies of the two player 1 types, it's optimal for player 2 to play right. And after having done this, so we can determine the Bayesian-Nash equilibrium by looking at what are the combinations of strategies that do not give any of the players an incentive to benefit by unilateral deviation. Now, one thing that we can see is that here we have all three numbers underlined. So the strategy, the combination of strategies where player 1 will play down, always, independent of his type, and player 2 will play right, that is an equilibrium. However, this is not a mixed strategy Bayesian-Nash equilibrium because player 1 will not mix. He chooses D always, and also player 2 will not mix. He plays R always. Now, player 1 type T is 6 playing down, player 1 type T is 0 playing down, and player 2 playing right. It's the only entry in the matrices where all three numbers are underlined. But there's a second case where two of them are underlined, and that's the entry that we have over here. Player 1 type T is 6 playing up, player 1 type T is 0 playing down, and player 2 playing left. Now this is a Bayesian-Nash equilibrium as long as 2p is at least equal to 1 minus p. And then we can solve for p, and we find that that holds as long as p is at least equal to 2/3. So then this is a Bayesian-Nash equilibrium as well, but we already knew that because it's exactly the solution that we found a couple of slides before. And this is a Bayesian-Nash equilibrium in pure strategies. So now we are ready to look for Bayesian-Nash strategies in, or Bayesian-Nash equilibria in mixed strategies. So let's do that. Again, these are the same matrices that we saw before, but I have made the entries corresponding to player 1 type 0 playing down. I marked them in gray to make life a little bit easier, because these are the entries that we have to focus on. Because if player 1 is of type T is 0, it's a dominant strategy for him to play down. So these four elements, they don't matter. So now suppose that player 1, if he's of type T is 0, he will choose D with probability 1. And suppose that when this player is of type T is 6, he will mix and he will choose up with probability Q. And player 2 will also mix and he will choose left with probability R. So then we get the following. So this is a decision variable, Q and R, and the P is given. It just determines the probability with which player 1 is of type T is 0 or T is 6. So player 1 cannot influence this probability, but this probability is something that the players can influence. Okay, so then the expected utility of player 2 of playing left is equal to, well, if he plays left, then either he ends up here or there. And this is the situation where player 1 type T is 6 plays up, which happens with probability Q. In that case, he gets the payoff of 2p. So the expected payoff is 2pq. And, well, if player 1 is of type T is 6, then his payoff is equal to 0. So the expected payoff of player 2 playing L is 2 times pq. Now suppose that player 2 plays right. What is his expected payoff in that case? Well, if player 1 is of type T is 6, then he will choose up with probability Q, in which case player 2 will receive a payoff of 4 times 1 minus P. So we have this term 4Q times 1 minus P. And if player 1 is of type T is 6 and plays down, which happens with probability 1 minus Q, then the payoff to player 2 will be equal to 4. So the expected payoff of player 2 of playing right is, well, if we simplify, 4 minus 4pq. And of course, it's our task to solve for p and q. Now going back, we know that if player 2 mixes in equilibrium between left and right, then the expected payoff of playing left must be equal to the expected payoff of playing right. So in other words, these two, they need to be identical. So we equate and we solve and we arrive at the equation Q is 2/3 over P. And now you might think, well, okay, what did we learn? Because we have still two unknowns, Q and P. We expressed one in terms of the other, but we did not find a solution. Well, in fact, we did, because the P is given to the players. It's a variable that is known, and only the Q is a decision variable. So this shows you that if Q or if P is at least 2/3, then player 1, when he's of type T is 6, he will choose U with probability 2 over 3P. And this condition, of course, is imposed because if we take P smaller than this value, then the probability Q will exceed 1, which is not possible. So that explains this condition over here. Now for player 1, given that he's of type T is 6, we can also compute his expected utility. Now if he plays up, then if player 2 plays left, then the payoff to player 1 will be equal to 6. So this one over here. That happens with probability R, because that's the probability that player 2 will play left. And if player 2 plays right, well, then the payoff of player 1 type T6 will be 0. So we have no second term here. And in case he plays down, then in all instances, independent on whether player 2 plays left or right, the payoff to player 1 type T6 will be 2. Again, if in a mixed strategy Bayesian equilibrium, the player 1 conditional being on type T is 6 will mix between up and down, then in that equilibrium, the expected payoff of playing each of these two actions should be the same. So we again equate, and we find that R is equal to 1/3. So we now found a solution. We have a Bayesian-Nash equilibrium in mixed strategies, and it's the pair of strategies where player 1, if he's of type 0, will always place down. If he's of type T is 6, he will mix, and he will choose up with probability 2/3 times P, and we know the value of P, and player 2, he will choose left with probability 1/3. When you do calculations like this, you can easily make a mistake, so it's always worthwhile to check whether you did everything correct. So let's check these expressions by plugging in a specific value for P, the probability that player 1 is of type T is 6. So we repeat the game over here, and we found in the previous slide that we have a Bayesian-Nash equilibrium in mixed strategies. And now we plug in a specific value. Take P is 3/4, which is larger than 2/3. For that value, probability Q is equal to 8/9. And then you can check that for player 2, he's indifferent between playing, given that player 1 follows his equilibrium strategy, player 2 will be indifferent between playing right or left. In both cases, his expected payoff will be 12/9. So please check that yourself. You can also check that for player 1, conditional on being type T is 0 and conditional on player 2 mixing with probability 1/3, that the expected payoff of playing up is 0, which is less than the expected payoff of playing down. So indeed, player 1, if he's of type T is 0, will play down for sure. It's a pure strategy. And if player 1 is of type T is 6, then you can check that the expected payoff of playing up is identical to the expected payoff of playing down, and in both cases it is equal to 2. So we find that this indeed is a Bayesian-Nash equilibrium, because given what the other player does, no player has an incentive to deviate from the given strategy. And that brings us to the end of another fascinating lecture. There's one other paragraph in the book about experimental games. So experimental economics, it's also one of the fields in which I'm an active researcher. One of the things that's done in experimental economics is to bring stylized games to the experimental laboratory and to see the extent to which the equilibrium predictions of these games are followed by subjects in the lab. So how well does the theory predict the decisions that people make in the empirical practice? So examples of games that have been brought to the lab are the dictator game. Now we saw an example of that in the previous lecture when we dealt with the Andreoni-Miller experiment, the prisons game, the ultimatum game, and all these games answer the question, okay, how do real people, often they are students, but also students are real people, how do real people play games? And more of this is discussed in the minor course, Behavioral and Experimental Economics. You may have taken that course. If not, well, if you are interested in this and you have another opportunity to take that course, then I really can recommend doing that. We're at the end of this lecture. Thank you again for your attention. This is a reference to the paper with the penalty kicks. You might read up on that one as well. And I hope you had an enjoyable couple of hours, and I wish you a very nice day.